Good morning, students. I welcome you to the discussion on the last topic in crystallography as per the Marine Science College for Women's Autonomous College syllabus. So, till now, I have discussed about crystallography in 13 sessions, and this is the 14th session in which I am going to discuss about liquid crystals. So, when you hear the term liquid crystals, the name itself indicates something interesting because the term liquid crystal has two words included in it. One is liquid, the other one is crystal. So liquids is one of the physical states of matter. Crystals is another physical state of matter. So two physical states are embodied in the same system. So when you hear the term liquid crystals, it comes to your mind that it is an intermediate stage of a solid wherein it possesses both liquid and solid characteristics. Hence, they are called as liquid crystals. And such a state, intermediate state, in which the solid possesses the liquid and solid crystal properties, is called as a mesomorphic state, and the phenomena is called as mesomorphism. I repeat, what is this mesomorphic state? We have learned in crystalline solids that crystalline solids possess sharp melting point. For example, if I take benzoic acid and heat it, when the temperature is equal to its melting point, entire benzoic acid is completely or abruptly converted to liquid state. That's the meaning of sharp melting point. So all the crystalline solids possess sharp melting point. In the sense, at a particular temperature, the solid is completely and in a single moment, the solid is completely converted into liquid state. That's the meaning of sharp melting point. Whereas amorphous sharp solids do not possess sharp melting point. For example, amorphous solid is a glass. So when you take a glass rod and heat it, glass rod upon heating does not abruptly melt into a pure liquid. Because glass is an example of an amorphous solid. So when glass rod is heated and a piece of glass is heated, the glass rod becomes hard. On further heating, it becomes soft. On continuous heat, on further heating, it becomes a highly viscous liquid. And as the heating is continued, viscosity of the glass liquid goes on decreasing, and ultimately at a particular temperature, it is converted into a true liquid, a pure liquid. So, amorphous solids do not possess sharp melting point, whereas crystalline solids possess sharp melting point. So, once we have a clear idea regarding the melting point of crystalline and amorphous solids, it's easy for us to follow what would be the nature of liquid crystal. So, as we already learned, liquid crystal state is an intermediate state where the solid possesses liquid as well as crystal solid properties. So, that state is called mesomorphic state. So, how do we obtain a mesomorphic state? For example, you have solid A. When solid A is heated at a particular temperature T1, it forms a turbid liquid. Upon further heating, at a further higher temperature, say T2, it could be converted to a clear liquid or fluid liquid. So, crystalline solids do not have this phase. At the melting point, crystalline solid is abruptly converted to pure or true liquid state. Whereas amorphous solids, they do not have these phases at all. Now, when you come to a mesomorphic system or a liquid crystal, the solids which exhibit this mesomorphic behavior when they are heated at a particular temperature, they are sharply converted into turbid liquid. I am using the term sharp. So at a temperature, here the example shown on the board, solid A at a temperature T1 is abruptly converted into turbid liquid state. Upon further heating at higher temperatures T2, the turbid liquid is abruptly changed into pure liquid. So these state changes that we come across are reversible, are perfectly reversible. When you heat solid A at temperature T1, it forms a turbid liquid. Upon further heating at a temperature T2, it is converted to true liquid. Now, these changes are reversible. So, heat the system above T2 degrees, then cool it. So, at T2 degrees, the true liquid is abruptly converted into turbid liquid. Upon further cooling, at T1, the turbid liquid abruptly changes into solid state. So, whatever changes that are observed in the forward process are exactly reversible. And this first temperature, wherein the solid is converted liquid state, is called as the transition temperature. And the second temperature, where turbid liquid is converted into clear liquid, is called melting point. So, unlike crystalline solids, where this intermediate state is absent, in the case of the solids exhibiting mesomorphism, we have this intermediate state. And the solids exhibiting mesomorphism or mesomorphic state need not have only one intermediate state. There could be more than one intermediate state also. For example, solid X at T1 changes to mesomorphic state 1. At the temperature T2, it changes to mesomorphic state 2. Then at T3, it can change to true liquid, or there can be one more mesomorphic state also. So, the solids which exhibit mesomorphism need not have only one mesomorphic state. There could be more than one mesomorphic state also. And one should remember that the solids which are exhibiting this mesomorphism phenomena are highly stable. They are as stable as other solids like your crystalline solids. So this phenomena of mesomorphism was first observed in the year 1888. This mesomorphic state was for the first time reported in the literature in the year 1888, and the first compound that was found to exhibit this type of behavior is cholesterol benzoate. So it's an ester of benzoic acid. Cholesterol, all of us are familiar with this term. It's an alcohol. So cholesterol benzoate is an example of a substance that exhibits mesomorphism. So this cholesterol benzoate, when heated, so the molecular form of this compound is C6H5 COO C27 H45. So this is a cholesterol benzoate. This is a molecule which is reported for the first time in literature exhibiting mesomorphism or liquid crystalline state. So this when heated to 145 degrees Celsius, it forms a liquid. And upon further heating of the 178 degrees Celsius, it forms a clear liquid. And this process is exactly reversible. Hence, we show it by reversible aroma. So, cholesterol benzoate at 145 degrees Celsius is called transition temperature, is converted to mesomorphic state or liquid crystal state. Upon further heating at 178 degrees Celsius, it is converted to clear liquid. So, 178 degrees is the melting point. And upon cooling, Clear liquid at 178 degrees Celsius is converted to a liquid crystal state. Upon further cooling at 145 degrees Celsius, turbid liquid is converted to pure solid state. So this is regarding the mesomorphic state. Then, if a solid is to exhibit this mesomorphism, what are the structural features that the compound should possess? So it is learned that usually the long chain compounds, as I see corresponding here. So usually long chain compound or high molecular weight compounds having a functional group like C double bond C, C double bond N, or N double bond N at the middle of the chain. So long chain compounds having these functional groups at the middle of the chain, and the compounds having OR or COOR as the terminal nodes. OR in the sense it could be ethers, COR it could be esters. So in general, long chain compounds having this type of functional groups at the middle of the chain or this type of terminal groups exhibit mesomorphism. And this mesomorphism can be brought about either by heating. So mesomorphic state can be obtained in two ways, by heating or by solvent intervention. By changing, by dissolving a sugar solvent. So, if mesomorphic state is obtained by heating, then we call it as a thermotropic, thermotropic crystals. If liquid state is obtained, or mesomorphic state is obtained by heating the solid, then such liquid crystals are called as thermotropic liquid crystals. And if the mesomorphic state is obtained by solvent diffusion, then are neotropic liquid crystals. So this is how mesomorphism or mesomorphic state can be obtained in two different ways. And when mesomorphic state is obtained by heating, we call it as a thermotropic liquid crystal. So these thermotropic liquid crystals, based on the structure and properties, have been classified. Classification of thermotropic liquid crystals. So thermotropic liquid crystals have been classified into symmetric liquid crystals, pneumatic liquid crystals, and polycystic liquid crystals. So the thermotropic liquid crystals are being classified into three categories, namely symmetric, pneumatic, and polycystic liquid crystals. I forgot to tell one thing. In mesomorphic state, why it's called liquid crystal state is that they possess both the properties of liquids as well as solids. When I say they possess the properties of liquids as well as solids, that is crystalline solids, the crystalline solid property that is exhibited by the liquid crystals is anisotropy. In the first session, when I was discussing about crystalline solids and amorphous solids, I stated that, I told you that crystalline solids are anisotropic. What's meant by anisotropy? The properties like refraction, density, conductivity, dipole moment, etc., when measured in different planes or along in different directions, the values of these properties are different in the case of crystalline solids. So that difference in physical properties when measured in different directions is called anisotropic property. And this anisotropic property of crystalline solids is due to regular arrangement or definite arrangement of particles in three-dimensional space. This anisotropy is absent in the amorphous crystals because there is no orderly or definite arrangement. So here in liquid crystal state or mesomorphic state, the matter possesses flow property like liquids and crystalline solid property like that is anisotropy. That is the difference. So now let us consider the types of these thermotropic liquid crystals one by one. Magnetic liquid crystals. So, symmetric liquid crystals. So, these liquid crystals do not flow as normal liquids. They have limited mobility. As I said, it's an intermediate state possessing liquid as well as crystalline solid properties. The first type of liquid crystals, symmetric liquid crystals, do not flow as normal liquids. When they are placed on the horizontal surface, they flow in such a way that in the form of layers. So the flow is such that the layers are gliding one over the other. So these liquid crystals, symmetric liquid crystals, when placed on horizontal surface, flow in the form of layers, and the flow appears as that the layers are gliding one over the other, and the flow of these symmetric liquid crystals is non-Newtonian. So what is this non-Newtonian flow? The flow of a liquid which does not obey Newton's law of viscosity are called non-Newtonian liquids. So, in our daily life, we come across these systems which are non-Newtonian liquids, where honey, any syrup, mayonnaise, cheese, butter, cheese, all these are examples of what? The systems which exhibit non-Newtonian flow. So, non-Newtonian liquids are those liquids which do not obey the Newtonian law of viscosity. So, the flow of these symmetric liquid crystals is non-Newtonian, hence the concept of viscosity is not applicable because the liquids which obey Newtonian law of viscosity will have same coefficient of viscosity at a given temperature. At a fixed temperature, eta, which is called coefficient of viscosity, is constant for true liquids or Newtonian liquids. But in the case of non-Newtonian liquids, eta, that is coefficient of viscosity, differs from one layer to the other. Hence, the concept of viscosity is not applicable to symmetric liquid crystals. Hence, it is called as they exhibit non-Newtonian flow. And when these symmetric liquid crystals are observed in very polarized light, you might be familiar with the words of polarized light because you studied steel chemistry in your earlier classes. So, polarized light is the light obtained when an ordinary light is passed through Nikon's prism. In an ordinary light, the vibrations of these photons are possible in all directions. So if you have this, you have the represented by normal light and ordinary light. When such light is passed through Nikon's prism, you get the polarized light where the vibrations are restricted to a single field. So when symmetric liquid crystals are placed in a plane polarized light or they are observed in plane polarized light, they are found to have a thread-like structure, which indicates that even in this state there is some order arrangement or there is some crystal structure. So when symmetric liquid crystals are observed in polarized light, they are found to have layer-like structure in the form of threads. They have thread-like structure indicating that there is some crystalline nature in the symmetric liquid crystal form. And like crystalline solids which diffract X-rays in all directions or along all planes. Even symmetric liquid crystals diffract X-rays but in one direction only. Unlike crystalline solids where X-rays are diffracted from different planes, in the case of symmetric liquid crystals, the diffraction of X-rays takes place only from a single plane or in a single direction. And these are not affected by magnetic fields. So these are the properties of symmetric liquid crystals. And the examples of symmetric liquids are ethyl para-hydroxy benzoate, then ethyl para-hydroxycinnamate. There are many examples I have taken only two. So these are the two examples of symmetric liquid crystals. So transition temperature and melting point for this. This is transition temperature and this is the melting point. So ethyl para-hydroxybenzoate has transition temperature 144 degrees Celsius and melting point of 120 degrees Celsius. And para-hydroxycinnamate transition temperature is 140 and melting point is 249 degrees Celsius. So this is about the symmetric liquid crystals. Now let us consider pneumatic liquid crystals. Second category. Pneumatic liquid crystals. So compared to symmetric liquid crystals, pneumatic liquid crystals have a higher fluidity. Means the flow of these pneumatic liquid crystals is almost similar to the normal liquid flow. Unlike symmetric liquid crystals where the flow is non-Newtonian, the pneumatic liquid crystals flow is Newtonian. Means the concept of viscosity, coefficient of viscosity is applicable. So, pneumatic liquid crystals exhibit Newtonian flow and concept of viscosity is applicable, which indicates that they are more liquid in nature than solid properties, whereas symmetric liquid crystals have lesser liquid properties and more of solid properties. So, pneumatic liquid crystals possess nearly normal flow and concept of viscosity is applicable, and the viscosity of these pneumatic liquid crystals is less than that of symmetric liquid crystals, and these are affected by magnetic fields. Symmetric liquid crystals are not affected by magnetic fields, whereas when pneumatic liquid crystals are placed next to magnetic field, they are affected. So what is the effect of magnetic field? So when these liquid crystals, when they are placed in extramagnetic field and observed in the direction of magnetic field, these turbid liquid crystals appear clear. I repeat, pneumatic liquid crystals are affected by magnetic fields. In the sense, pneumatic liquid crystals, which are nothing but turbid liquids, when they are placed on external magnetic field and observed in the direction of magnetic field, these turbid liquid crystals appear as clear liquids. The moment magnetic field is cut off, again turbidity appears. So, pneumatic liquid crystals, when placed in an extramagnetic field and observed in the direction of magnetic field or along the lines of magnetic force, they appear clear, and the moment magnetic field is cut off, they appear again turbid. And pneumatic liquid crystals, examples are para, azoxy, and so. Anisole is liquid ether. So when the transition temperature is 160 degrees and melting point is 1.5 degrees, this is transition temperature. This is melting point. Then para, azoxy, phenol. 137 degrees and 167 degrees. And para, methoxycinnamic acid. 170 degrees and 186 degrees. Okay, so and when these nematic crystals, when absorbed in polarized light, they are found to possess thread-like structure. I'm sorry, symmetric liquid crystals possess fan-like structure, whereas please make a correction. I said symmetric liquid crystals, when observed in polarized light, I said they have a thread-like structure. I'm wrong, sorry. They possess fan-like structure, whereas nematic liquid crystals possess thread-like structure. So these are the properties of nematic liquid crystals. So it is easy for you to remember the properties of symmetric and nematic liquid crystals in the form of comparison. We make a table of a comparison between symmetric and nematic liquid crystals. The third category of liquid crystals is the cholesteric liquid crystals. So what are these cholesteric liquid crystals? These liquid crystals possess both symmetric as well as nematic liquid crystal behavior. So, sorry, cholesteric liquid crystals. So, this third category of liquid crystals, namely cholesteric liquid crystals, which have both symmetric and nematic liquid crystal property or liquid crystal character. So, even these have layer-like structure like symmetric liquid crystals, but thickness of the layers of cholesteric liquid is higher. The thickness is about 500 to 5,000 molecules thick. That's the difference between the thickness of symmetric and cholesteric liquid crystals. So it's less than 500 molecules thick in the case of symmetric liquid crystals, whereas cholesteric liquid crystals, which do have a layer-like structure, but thickness of the layer is ranging from 500 to 5,000 molecules thick. And the examples of this cholesteric liquid crystals are cholesterol benzoate, then cholesterol formate, all esters of cholesterol and cholesterol mixate. These are the examples of cholesteric liquid crystals, and these exhibit strong color effects. These show strong changing colors in polarized light. So this is about the classification of liquid crystals. Now let us consider molecular arrangement in these liquid crystals, namely nematic and symmetric liquid crystals. Okay. When it comes to arrangement of molecules or molecular arrangement in liquid crystals, this is schematic representation of a molecular arrangement in symmetric, nematic liquid crystals and true liquid. So when you look at molecular arrangement in symmetric liquid crystals, we have a parallel layer arrangement. So the molecular arrangement is nearly in the form of parallel layers, and within each layer there is a regular spacing, and even the distance between the successive parallel layers is also almost the same. So when it comes to molecular arrangement in the case of symmetric liquid crystals, It has almost a regularly arranged structure as like a crystalline solid. Hence, they are more solid-like than less liquid-like character. And I also said that the flow is restricted, it's non-Newtonian, concept of viscous is not applicable because of this type of arrangement of particles. So it's a layer, there's arrangement of particles in the form of layers which are parallel, and even the distance between successive layers is almost the same, and the distance between the particles in the same layer is also it's regularly fixed. When it comes to nematic liquid crystals, here also the molecular arrangement is almost parallel, but the layer-like arrangement is absent. Unlike spectacle crystals, in nanometer crystals where there is a parallel arrangement of molecules, but it's not in the form of layers. And arrangement of molecules is irregular, it's not layering, and therefore they have more freedom for the flow. Hence, they are more fluid in nature than spectacle crystals. And when you look at this true liquid crystals, the molecular arrangement is completely random. So there is a difference in the molecular arrangement of liquid crystals from that of true liquid, and also there is a difference in molecular arrangement of smetic from that of nematic liquid crystals. So this is about the molecular arrangement in the case of smetic and nematic liquid crystals. Now the last topic is applications of liquid crystals. So all of us are familiar with LCD TV, LCD screens, etc., etc. So first and foremost application is in the field of liquid crystal display. So we have calculators, computer monitors with liquid crystal display, mobiles with the liquid crystal display, TVs with the liquid crystal display. Now we have latest LEDs, okay, light emitting diode systems. So liquid crystals are most widely used in liquid crystal display systems. Number two, liquid crystals also are used in monitoring body temperature. And liquid crystals are also employed in knowing the faults in the joints of metals. So these are some of the applications of liquid crystals. With this, we come to the end of discussion on crystallography prescribed for third semester students of Maharani Science College for Women Autonomous. Myself. Thank you.